If you haven't watched my previous video, I would recommend doing so because I introduced the hyperbolic trig functions there, the main topic of this video. You might be somewhat lost if you aren't aware already of the fundamentals of the hyperbolic trig functions. And welcome back to PyGuy. Today I'm going to be talking about hyperbolic trigonometry again, but this time talking about the geometric definitions. This is sort of the analog to the unit circle from the regular trig functions, but I think this is a lot simpler. It just doesn't go as in depth. So I start here by graphing the unit hyperbola. This type of shape is a hyperbola. And it's defined by x squared minus y squared equals 1. The name of it doesn't really matter, but we just care about this shape. For the most part, though, we don't necessarily care about the left half here. I will graph its asymptotes just to show you what it looks like. The graph tends towards these lines here at infinity, but they're not super important to what we're talking about right now, so I'll just get rid of those. What we have here is the point hyperbolic cosine of A, comma, hyperbolic sine of A. So the distance between the y-axis or the horizontal distance, I should say, between the y-axis and this point is the hyperbolic cosine of whatever arbitrary number we're choosing. Right now it's 1, so if I adjust this slider, now the distance from here to here is the hyperbolic cosine of 1.6. And then the same for the hyperbolic sine. The distance from here to here, the vertical distance, is the hyperbolic sine of 1.6. And this is very similar to the regular trig functions, where in the unit circle you have cosine of A, sine of A, but this time we have the hyperbolic sine. So just like the unit circle, you can drag this slider and it will trace the hyperbola. It doesn't matter what the point is, as long as the numbers match, it'll trace the right half of the hyperbola. Hyperbola. The main part of this is if you connect the origin to this point, and this is the equation for that line. I just put it in point slope form and then just put x on the end to make it a function that you can. So even if I drag this slider, the line will adjust with the point. So this is connecting the origin to the point cosine or hyperbolic cosine of A, hyperbolic sine of A. I'll label it there. The important part is that the area in between this purple line, the red line, and the black line is going to be whatever A is divided by 2. So right now the area bounded between the purple line, red line, and black line is 1/2 because I have A set as 1. Now remember, this point is not 1, 1. It's hyperbolic cosine of 1, hyperbolic sine of 1. So those will be irrational numbers because we're dealing with E. If I change it, say I make it 2, it's pretty far up there. It gets very thin up here, but the area bounded between these three curves will be 1 because 2 divided by 2 is 1. Now if I make it negative, this is just considered to be negative area if it's below the x-axis. So the area here is negative 1/2. So the unit hyperbola can actually tell us a lot of things about the hyperbolic trig functions. Like I said, it's very, very similar to the unit circle. This is the shape that geometrically defines the hyperbolic trig functions. So in the unit circle, both the cosine and sine can be negative and positive because it loops around and has that periodic behavior. But what you'll notice here is that for all the numbers, for any number A, the hyperbolic cosine is going to stay to the right of the y-axis, which means that it's never going to be negative. And what you'll notice here is that its minimum is at 1, 0. So, but in this case, the hyperbolic cosine is the x value. So that means that the hyperbolic cosine's minimum value is 1. And we can graph this and confirm that this is in fact the case. And there it is right there. 1 is its minimum y value. Of course, it's flipped here because we have cosine set to be x. But the point stands. But what you will notice as well is that the sine can be negative. It can go below the x-axis. And then we graph that, and we see that that is in fact the case. But we know this fact for the exact same reason that we know that the minimum and maximum values of the regular sine and cosine are 1 and negative 1. Because if we go in and we graph the unit circle here, x squared plus y squared equals 1 is the equation. And notice, though, that the x squared plus y squared equals 1 is not very different than the unit hyperbola equation. It's just a plus and minus that's making the difference here. And then we'll put a point here. Okay. And then we can slide our unit circle point all around here. Just ignore the line. I have the same variable mapped to two different operations here. But look, if the cosine of x, or the cosine of a, sorry, is going to be the horizontal distance, the furthest back can go is -1, and the furthest forward it can go is 1. So we know the maximum and minimum values of the cosine function are 1 and -1, and then it's the same thing for the sine. Now, the reason that the hyperbolic trigonometric functions are not periodic while the regular ones are is because the circle will just loop around the point will just loop around the circle for infinity if you go that far forward and backwards. Whereas the cosine dot will just move along the hyperbola and go downwards. It's not repeating any values. So that's why the regular trig functions are periodic and the hyperbolic ones are not. And notice then that's why they're called the hyperbolic trigonometric functions. They are defined by a hyperbola, hence the name. Now, the other four don't necessarily have a neat geometric definition along the hyperbola, and this is similar to the regular trig functions, where they're just kind of defined as the reciprocals and quotients of the sine and cosine, and that's the case here too. There's no really neat geometric definition on the unit hyperbola for the hyperbolic tangent, cotangent, secant, and cosecant. Lastly, I just want to spend a few minutes talking about why some of the graphs of the equations look the way that they do. So I'll start with all the equations that don't have an asymptote, or don't have a vertical asymptote, I should say, which is the hyperbolic sine, cosine, tangent, and secant. The reason being that sine, remember, and cosine actually are both defined as being e to the x plus or minus e to the negative x all over 2. So obviously 2 is a constant in the denominator. It will never equal 0. You'll get a vertical asymptote whenever the denominator equals 0, because you'll have a divide by 0 error. And that will never happen for equations that have a sine or a cosine. So therefore you'll never get a vertical asymptote. But what about the hyperbolic tangent and the hyperbolic secant graphs? They do have x's in the denominator, but there's a reason why they do not have asymptotes. So the equation for tangent of x with e in it is this. It's it's the sine over the cosine. So it's e to the x minus e to the negative x all over the cosine, which is e. Ooh, that's not what we want to do. All over e to the x minus e, or plus e to the negative x. Okay. I'll turn everything off here. And yes, that should match perfectly. Now, the reason that this won't ever have an asymptote is because this bottom portion won't ever equal 0, because it's an addition. So there's no way that e to the x by itself can equal 0. If you had e to the x minus e to the negative x in the denominator, you can make e to the x be 1 and e to the negative x also be 1. And then it's a subtraction. So 1 minus 1 is 0, and therefore you have a vertical asymptote. But e to the x can never equal 0. This can be very clearly shown if we graph the logarithm. If you're familiar with logarithms, this is a vertical asymptote, so this will never touch 0, which means that e to the x will never touch 0. If you're not familiar with logarithms and that doesn't make any sense, that's fine. All you need to know is really that e to the x can't equal 0. But if you are familiar with logarithms, that's the reason why. And that is actually the reason why the hyperbolic cotangent does have an asymptote, because this equation is flipped. The numerator and denominator are flipped. So this part is on the bottom. And like I said, you can make e to the x and e to the negative x both be some same number, 1 for example, and then subtract them. But since these can't equal 0, since each individual piece can't ever touch 0, and as addition, you're always going to be increasing from the one piece, this bottom part can never be 0. The only reason this can be 0 is because it's getting lower, because it's subtraction. And that's the reason why the hyperbolic secant also doesn't have the asymptote, because this is just 2. If I want to get rid of that. No, not the entire thing, just the top part. Yeah. So that's just a constant that doesn't do anything there. Well, it does something, but it doesn't do anything to really give it an asymptote. And yeah, that's the reason why the hyperbolic cotangent does have the asymptote, because it's the tangent graph flipped. And then the same thing for the hyperbolic cosecant. The hyperbolic cosecant is that. And you see that it has an asymptote because, like I said, it's the subtraction. Each of these pieces individually won't be 0, but when you subtract, you can get it to be 0. And then you have a divide by 0 error, and therefore it has an asymptote. So that explains why certain graphs have asymptotes and certain ones do not, because of the way the e to the x and the natural logarithm graph function. So that's really why I think that the hyperbolic trig functions are so interesting. You know, to get earlier I was talking about the trig, the unit circle, the trig functions, you know, a lot of really interesting algebraic tricks, and this whole thing about asymptotes and connecting it to the natural logarithm graph. It's all very, very connected. That's why I think math is so great and interesting to study, because everything is connected. And that's kind of the point of the entire channel of Pi Guy, really, to just show off some really awesome math concepts that tie everything together like this one. Of course, this is not the last video in the hyperbolic trig series. Next time, I will be talking about problem solving and how hyperbolic trig functions can be used as shortcuts in certain problems. So I hope you will watch that video and join me there. Very excited. But for the meantime, thank you for watching. Please feel free to like, comment, and subscribe. And leave a suggestion of what videos you'd like to see after the hyperbolic trig series is concluded. I'd be eager to hear of your ideas. But yeah, that's it. Thank you for watching. Have a great day.